All right, I just got the email from UH administration saying the in-person course will resume January 31st. Okay, so next week we will still have online class. Okay, so postponed by one more week. Right, so I think our first in-person class will be Monday, February 1st. Okay. All right. So today we'll start chapter 2. Okay. Chapter 2 is called probability, which is obviously very, very important chapter. We will learn what is counting method, how to calculate the probability for a certain experiment. Yeah. So again, let's do some review for definition. Again, experiment is a process resulting in an outcome that cannot predict it in advance with certainty. Okay. For example, roll a die. We know for a die we have 6 possible outcomes: 1, 2, 3, 4, 5, and 6. I'll toss a coin. We have 2 possible outcomes. We have head or tails. Okay. Or will be the content of a box of the series. So that's the weight of the series in ounce. Okay. So these are examples of experiment. How we can get the probability for certain outcomes for this experiment. For sample space, I think we discussed this before. The sample space is a set of all possible outcomes of experiment. For example, rolling a die, the sample space will be 1, 2, 3, 4, 5, 6. Yeah. And for toss coins, the sample space will be heads and tails. So only 2 possible outcomes for this coin tossing experiment. Within a cereal box, the sample space in cereal should be from 0 to infinite ounce, or for more reasonable, for 16-ounce box, let's say between 12 to 20 ounce. So it should cover all the possible outcomes for that weight. A subset of sample space is called event. Okay, we also discussed that last time. Okay, for example, roll a die, an event can be defined as we got odd number. So that sample space for that event will be 1, 3, and 5. Okay, for even number, will be 2, 4, and 6. Okay. So when the experiment performed, an event either happens or it doesn't. For example, if you toss a coin, the event we got head either happens or not happens. And for any sample space, empty space, we read as this, is also an event. Okay, so that's the opposite of entire sample space, which include all the possible outcomes for that event. Okay. A given event is said to have occurred if the outcome of an experiment is one of the outcomes in that event. Okay. For example, if a die come up with a 2, then this event, 2, 4, 6, means the event we get the even number. Okay, because 2 belong to this event, so the event of even number will occur. And also this event, so this event including 1, 2, and 3. So we can say this event is defined as we get number less than 4. Okay, so event get less than 4 also occurs because 2 include in this event, along with any other event that contain outcome 2. Okay. So more example of event experiment. If we see experiment is defined as we record the age of person. So event A is defined as a person is 30 years old, and B is person is older than 65. Okay, so if we pick up person and the age is 29, okay, then event A doesn't happen, and event B also doesn't happen. Okay, if a person is 70 years old, then event B will occur because 70 is older than 65. Okay, so simple enough. Toss a die. Event A, for example, we observe odd number 1, 3, 5. Event B, we observe number greater than 2. So greater than 2 will include 3, 4, 5, and 6. Okay. Now let's look at a little bit more complicated example. So we have an electrical engineer has 2 boxes of resistors. Okay. For each box, we have 4 resistors. Okay. And the first box is labeled 10 ohms. Okay. But the actual 4 resistor has the actual resistance of 9, 10, 11, and 12 ohms. And resistor in second box labeled in 20 ohms, but actually we have 18, 19, 20, and 21. Okay. And he needs to choose 1 resistor from each of these 2 boxes and determine the resistance of each. So if we define A as the event that the first resistor has resistance greater than 10, and B is the event that the second resistor has resistance less than 19. Okay. And C is another event. The sum of the 2 resistors from these 2 boxes is equal to 28. Okay. So first of all, let's find out the sample space. Okay. So the sample space is this. Okay, so how we can get the sample space? So again, the sample space is all the possible outcomes for that experiment. Okay, so we pick 1 resistor from box number 1, which is labeled at 10 ohms. And then the second step, we pick another resistor from the second box, which is labeled as at 20 ohms. Okay, so these are the possible outcomes. So let's look at the first 4. When the first resistor from the first box is 9, so we could have 918, 919, 920, and 921, right? If the first step we get a 10 from the first box, then we also have 18, 19, 20, and 21. If the first is 11, we also get 18, 19, 20, and 21, and so does when the first resistor is 12. Okay, so for that experiment, we have 2 steps. The first step, we pick 1 from the first box. The first step, we have 4 possible outcomes, so 9, 10, 11, and 12. Okay. And the second step, we also have 4 possible outcomes, which is 18, 19, 20, and 21. Next class will show you how we can count how many possible outcomes for a certain experiment. We can use 4 times 4 in this case, so we have totally 16 possible outcomes. So let's say we get this sample space already. Then let's write down what event A, B, and C. Okay, so event A is the first resistor has resistance greater than 10. Okay, so more than 10 is 11. So we have 4, and also 12. Okay, so under 11, we have 11, 18, 11, 19, 11, 20, and 11, 21. And so does under 12. Okay, so for event A, we have 1, 2, 3, 4. We have totally 8 possible outcomes. Right? So B is event that second resistor has a resistance less than 19. Okay, so less than 19 has only one way, which is 18. Okay. Because for the second box, the resistance are 18, 19, 20, and 21. So only 18 is less than 19. Okay, so event B will be 9, 18, 10, 18, 11, 18, and 12, 18. And C is the event that the sum of the resistance is equal to 28. So how we do that? Go back to the sample space. We add the first and second together. The first one is 27. Second one is 28. So that is belong to C. The third one is 29, not. And then we count, the next one will be 10, 18. So 10 plus 18 is 28. So we have two possible outcomes for event C. Okay. All right. So questions so far for this experiment? Let's go back to the old example of toss the die. Then event A, if we define as we observe an odd number, then it will be including 1, 3, and 5. Event B, we observe a number less than 3, so that will include 1 and 2. Okay, so if we get 1, so 1 is odd number, so event A occurs. 1 is also less than 3, so event B also occurs. So when the phase shows the 1, both event A and B occurs. All right. And these are all the simple events. E1, we observe 1. E3, we observe 3. And all the simple events together, we call that sample space. Sample space. Okay. So two events we call mutually exclusive. If one event occurs, the other event cannot occur, and vice versa. For example, toss the die. If we say event A is we get odd number, so odd number is 1, 3, and 5. Event B we say is we get even number, so 2, 4, and 6. So then these two events A and B are mutually exclusive, because if the upper phase is odd number, then it cannot be an even number, and vice versa. Okay, so mutually exclusive. And event A and B can be further decomposed into simpler events, which are also mutually exclusive. So event A is we got odd number, can be decomposed into E1, we get 1, E3, we get 3, and E5. Okay, and these three simple events are mutually exclusive. And event B is we get number less than 3, can be decomposed into E1 and E2, right? A simple event is an event that cannot be further decomposed. For example, E1. So we get number 1, that's the simple event, because it cannot be further decomposed to even simpler events. Okay. So E1 is a simple event. And sample space is a set of all mutually exclusive simple events. For total die, the sample space will be E1, E2, E3, E4, E5, and E6. And the event is a collection of one or more simple events. Again, the die problems. The simple event is this 6, E1 to E6, right? And sample space, S is for sample space. We can write like this, or we can draw something like this. S is for sample space. Within the sample space, we have 6 simple events. So all possible outcomes together is called sample space. An event is a collection of one or more simple events. So event A, odd number, so that will include 1, 3, and 5. Okay. Event B is a number larger than 2. Okay, larger than 2 will include 3, 4, 5, and 6. Okay, so from here we can see event A, which is the green area, and event B is the striped area, and they have some intersection, which include 2 events, E3 and E5. Okay, so E3 and E5 is called intersection of event A and B, which means when E3 or E5 occurs, event A and B both occurs. Okay, so that's called intersection. A union of 2 events and A and B, we also denoted as A or B. So this is half circle facing up. Okay, is set of outcomes that belong to either A, B, or both. Okay. So word A or B means, we can write A or B or A half circle facing up. So the event A or B occurs whenever either A or B or both occurs. So in this experiment, okay, A or B will be include E1, E3, E5, E4, and E6. Okay, so we have 5 possible outcomes for A or B. So anything belong to these 2 circles, it's called A or B. E2 is outside A or B. Okay. Again, we call that union or half circle facing up. We also call that A or B. That means whenever either A or B or both A and B occur. Okay, so that is union. So these 2 events, what is A or B? Right. For this event, we have event A, we have 1, 2, 3. Event B, we have 2, 3, and 4. Okay, so event A or B, okay, will be 1, 2, 3, and 4. Okay, do not write 2 twice, and do not write 3 twice. Okay, so event A or B will again include 1, 2, 3, and 4. Okay, either A or B or both occurs. Any questions about union? Okay, so that is A or B or union. The next is intersection. So intersection is the kind of opposite of union. So intersection of two events A and B we write as A and B. This is half circle facing down. Is a set of outcomes that belong to both A and B. Okay, so that two circle, the intersection of the two circle, is called A and B. Okay, so event A and B occurs whenever both A and B occur. So for example, here A and B will include what? Both A and B occur. E3 and E5, right? So that is intersection, or A and B. A or B or the union is all these areas covered by these two circles. Okay, this is a very, very important concept, union and intersection. Event A, 1, 2, 3, event B, 2, 3, 4. What is A and B? Again, half circle facing down is and. Okay. So both A and B occurs is 2 and 3. Okay, so A and B will include 2 and 3. So that's union and intersection. Complements. Complements is right as AC. So C is for complement. So that's the set of outcomes that do not belong to A, also called not A. Okay. So even not A occurs whenever A does not occur, right? Okay. So that's called complement or not A. Okay. So if A is below the number 6, what is complement of A or not rooting of 6? Okay. Not rooting of 6 will include 1, 2, 3, 4, and 5. Okay, so AC will include 1, 2, 3, 4, and 5. Okay, so that's complement. If two events A and B have nothing in common, okay, so nothing in common means these two events, these two circles has no interaction. Okay, then we said these two events are mutually exclusive. In other words, if A and B are mutually exclusive, then P, A, and B, okay, so P is for probability. A half circle facing down is and B. Okay, if A and B has no intersection, and the property of of P, A, and B equal to 0, then we call these two events mutually exclusive. Okay. If we have more than 2 events, A1, A2, and AN, if no two of them has any outcome in common, so we say these n events are mutually exclusive. Okay. That's another name for this. It's called disjoint event. So basically means there's no intersection for these n events, A1, A2, AN, no intersection. Okay. Okay. Again, use the toss the die experiment. Okay. So let's say event A is we get odd number, and event B is number greater than 2. Okay, and these two events are not mutually exclusive. Okay, because all numbers include 1, 3, and 5. Number greater than 2 include 3, 4, 5, and 6. So these two have something in common, include 3 and 5. So if we get a 3, so 3 is odd number, so event A occurs. 3 is also greater than 2, so event B also occurs. And so does 5. 5 is odd number, 5 is also greater than 2, so they are not mutually exclusive. Event C, we get number 6. Event D, we get number 3. These two events are, of course, mutually exclusive. Upper phase is 6, so it cannot be 3, and vice versa. So how about event B and C? Okay, event B is more than 2, so 3, 4, 5, and 6. Event C is we get 6. So event B and C are not mutually exclusive, because if we get number 6, event B occurs. So does event C. Okay. How about B and D? D, observe number 3. So if we see a number 3, D occurs. 3 is also more than 2, so B also occurs. So B and D are not mutually exclusive. Okay, so you get the idea. Then let's go back to the toolbox of resistor experiment. Here are some of the questions trying to answer. So is it possible for event A and B both to occur? How about B and C, A and C? And which pair event is mutually exclusive? Okay, so that is event A, event B, and event C. Okay, so is it possible for event A and B both to occur? Okay, let's see if there's anything in common between A and B. One thing in common is this, 11 and 18. Okay, 11 and 18 occurs, then both event and B, A and B occurs. So they are not mutually exclusive. And also 12 and 18. Okay, so 12 and 18 also occurs both in event A and event B. Okay, so yes, it is possible for both event A and B to occur. Let's look at event B and C. Is there anything in common for event B and C? Okay, yes, 10 and 18. Okay. So event B and C are not mutually exclusive. If we try to find out what is A or B, half circle facing up, again, we call that A or B, okay, or the union. Okay, so what we do is we copy everything from A down here, and then we copy everything from B down here, but we do not repeat anything in common. Okay, for example, 11 and 18, it occurs in both A and B, so make sure you only write it once. Okay, do not repeat 11 and 18. Okay, so this is A or B. And what is A and B? So half circle facing down is A and B. Then we just pick what occurs in both A and B. So we have 2, 11 and 18, and also 12 and 18. Okay, So that is A or B. So as we can see from here, A or B belong to A. A and B belong to A or B. Or in other words, A or B include A and B. Okay. It is very clear if you see from here. So again, what is A or B? So A or B including everything within the areas of A and B. So that will include E1, E3, E5, E4, and E6. A and B, on the other word, it is intersection between these two circles, A and B. Okay, so that's E3 and E5. So A or B include A and B. Okay. Any questions so far about this intersection and union? And more practice, what is BRC and what is BNC? Okay, so BRC, again, what we do is we copy everything from B down here and copy everything from C down here. Remember, do not repeat any events. Okay, so do not repeat 1018 here. Okay, 1018 occurs twice, but we only write it once. Okay, so that's BRC. BNC, 1018. And that's BNC. Okay, so I think right now everybody get the idea what is intersection and what is union. Okay, more practice. A or C. Again, we copy everything from A, everything from C, but we do not repeat anything in common. Okay, but A and C has nothing in common. Okay, because look at A and C, they have nothing in common. Then we see A and C is empty space. We write like this. So this means empty space. None. Okay, let's continue. Then we talk about probabilities. Okay, so this chapter 2 is about probability. So probability is defined as each event in a sample space, they have a probability occurring. Okay, and it is a quantitative measurement of how likely the event is to occur. Okay. For example, if we toss a die, then the chance we get head is 50%. Okay, everybody knows that, but why it is 50%? Okay. The expression P means probability that event A occurs, and it is defined as the proportion of times that event A would occur in the long run if we repeat this experiment over and over again. Okay, so that is probability. So let's say if we perform experiment n times, and the relative frequency of event A is the number of event A occurs over n times. Okay, so if n occurs k times, then it is k over n. Okay, so that is relative frequency of event A occurs. If n is infinitely large, that is the definition of PA. So PA is probability of event A occurs is the limit when n approach infinite. Because it is a probability, probability is a number between 0 and 1. So 0 means zero chance A will occur. 1 means 100% every time event A will occur. Okay, so must be between 0 and 1, inclusive. And the sum of the probability that all simple event in S is the sample space, of course, equal to 100%. Okay, all the possible outcomes, the probability added together is 100%. We toss the coin. So the chance we get head is 50%. The chance we get tail is also 50%. So 50 plus 50 is 100%. So all the simple events added together always equal to 100%. And the probability of event A is found by adding the probability of all the simple events belonging in A added together. Okay. So for example, for event A, for toss a die, if A is defined as we get odd number, okay, then probability event A occurs will be the probability we get 1, the probability we get 3, and the probability we get 5. Yeah, A and C result in empty space. That's nothing. As a 0 is a cross. Okay, it's not a 0, it's a empty, nothing. Yeah, thank you. Grant. All right, so axioms of probability. So this is universally accepted principles. Okay, so S is the sample space. Sample space include all the possible outcomes, all the possible simple events. So P, the probability for the sample space will equal to 1. Okay, so that's true. And also probabilities between 0 and 1 inclusive. Okay. And if event A and B are mutually exclusive events, then this is PA half circle facing up is union or. So PA or B is equal to PA plus PB. Okay, so this equation holds true when A and B are mutually exclusive. In other words, remember the two circles of A and B. When A and B, these two circles has no interaction, they have nothing in common, then we can use this equation. So what will happen when they have something in common? When they have an intersection? Okay, we're gonna discuss the equation in a moment. When A and B are mutually exclusive, then PA or B is equal to PA plus PB. If we have more than 2 events, then this also holds true. For any event A, PAC, what is PAC? C is for complement. Okay, so AC means complement of A or not A. So here means the probability A not occurs is equal to 1 minus the probability A occurs. If we move PA to the left side, so that becomes PA plus PAC equal to 1. So means the probability of A occurs plus the probability of A not occurs equal to 100%, of course. Okay, so toss the coin, the probability we get a head, 50%. The probability we not get a head, which is a tail, by the way, is also 50%. So these two added together is equal to 100%. Okay. This is empty set, means nothing, doesn't mean 0. Okay. The probability of empty set is equal to 0. which means the probability of nothing happens is 0. We toss the die. Possible outcomes is head and tail. Okay. Nothing else. If A is an event, include outcomes O1, O2, and On, then the PA will be equal to PO1 plus PO2 plus PON. Okay. So when a sample space has equally likely outcomes, okay, then how we can calculate the probability? Okay, there's a many situations that a sample space with equally likely outcomes. Okay, for example, we toss a die. We have 6 possible outcomes: 1, 2, 3, 4, 5, 6, and each of these 6 outcomes, they are equally likely outcomes. You know, as long as the die is a fire die. Okay, so each event has 1/6 chance. A particular important case is the random selection of item for a given population. Okay. So a population from which an item is sampled at random can be thought of as a sample space with equally likely outcome, such as a lottery. Okay, or we toss a coin, or toss a die. Okay, so if S is a sample space with unequally likely outcomes, so toss a die, the sample space is 1, 2, 3, 4, 5, 6. And each of these 6 outcomes are equally likely outcomes. Okay, then PA is equal to K over N. All right, so that's the definition. Then let's look at another example. Okay. So we have extrusion die is used to produce the aluminum rods. Okay. For the specs of the rods, we have the diameter, and we also have a length. Okay. For the length, we can classify it as too short, okay, which is good, or too long. For the diameter, we also has too thin, okay, and too thick. Totally, we have a population of 1,000 rods. Okay, and here shows the number of rods in each class. For example, we have 900 rods are okay in both length and diameter, and we have 25 are okay in diameter, but it is too long. Okay, added together, 1,000 rods. So a rod is sampled at random from this population, 1,000 rods. What is the probability that is too short? What is the probability is too short? Okay, too short here. Okay, for too short, it include too short and too thin, which is 10. Too short and okay, 3, and too short and 5. Too thick, which is 5. Okay, so the probability that is too short is how much? It is all equally likely events. It will be 10 plus 3 plus 5, which is equal to 18, divided by the whole population, which is 1,000. Okay, so that is the probability that a randomly chosen rod is too short. Make sense? So if A event is the event containing n possible outcomes, O1 to On, okay, then PA is equal to PO1 plus PO2 plus PON. Okay. We just discussed if two events A and B are mutually exclusive, then PA and B will be equal to PA plus PB. But here is what will happen, what equation we're going to use if A and B are not mutually exclusive. So that is equal to PA plus PB minus PA and B. Okay. Obstacle facing down is and or intersection. So go back to the rod problems. Okay. If a rod is randomly chosen, what is the probability that it's either too short or too thick or both? Okay. It's too short is these three possible outcomes, 10, 3, and 5. Okay. Too thick is these three. Include too thick, too short, too thick, okay, and too thick and too long. Okay. And we can see these two events have intersection. Okay. So when this occurs, so that means it is both too short and too thick. So when this 5 occurs, both event too short occurs and event too thick occurs. Okay, so if we want to use the equation in the previous slides, we need to minus intersection of these two events, which is 5 over 1,000. Okay. Let me write this down. Okay. Let me share my notes. Okay, here. All right, so either too short or too thick or both. So too short, it is this 3, okay? And too thick, it is this 3. And we can see 5 is the intersection. Okay. So using this equation, we calculate the probability is either too short or too thick or both. So that is here. So that's equal to PA if we say A is too short. Okay, then PA will equal to what? So 10 plus 3 plus 5 over 1,000, right? So 10 plus 3 plus 5 over 1,000. Okay, and PB, if we define as too thick, will be 5, 4, and 13. Okay, so 5 plus 4 plus 13 over 1,000. So that is PB. And we need to minus PA and B. Why minus PA and B? So look at this. We add number 5 twice. Okay, we add intersection of A and B twice. So we counted it twice. It's not fair. We need to minus that intersection. That's why we need to minus PA and B. So what is PA and B? That is 5 over 1,000. Okay. And if we put this in this diagram, A will include 10, 3, and 5, and B will include 5, 4, and 13. Okay, so from here it's very clear why for P, A, or B, we need to use this equation. Why we need to minus that intersection here, because we counted it twice. All right, so questions so far about this. So make sure everybody understand the concept. Okay, when A and B are not are mutually exclusive. So when these two events, let's see, have nothing in common. This is A and B. These two circles has no intersection, nothing in common. Then P, A, or B will simply be PA plus PB then.
Professor?
Yes, Grant.
I'm just wondering as to where the 1,000 comes from.
The 1,000 is coming from the whole population, right? So we have totally 1,000 rods, and you want to know what is the randomly chosen rod is too short.
Oh, okay.
Right? You have 18 out of 1,000. So that is 18 divided by 1,000. Yeah.
Okay, I get it.
Yeah. Good question. Okay. A new example. Right. So we have a target on a testing fire range. Okay. So consists of a bullseye with two concentric rings around it. Okay. So a projectile fire the target. The probability hit the bullseye is 10%. So let's draw something here. So let's say this is the bullseye. This is one ring. This is another ring around it. So hit the bullseye here, it is 0.1. The probability hit the inner ring. The inner ring is here, this ring. Okay. For this ring is 25%. And probability hit the outer ring is here, outer ring. Well, this is 0.45. Okay. So what is probability the projectile hit the target? So anywhere within the target, we see it hit the target. Okay. So simply, P we hit the target is equal to the probability hit the bullseye. Let me just write down 0.1 plus the probability hit the inner ring, 0.25, and probability hit the outer ring, 0.45. Okay, so that is 0.8. 80% chance projectile will hit the target. Anywhere within that target will count. Then the probability that miss the target, okay, so that means not hit the target or complement of hit the target. So the probability miss the target means, of course, will be 100% minus the probability hit the target, which is 0.8. Okay. Right. So here is another example. So in process manufactures aluminum cans. Okay. The probability a can has a floor on the side is 2%. Probability the floor on the top 3%. And probability has a floor on both side and the top is 1%. Okay. So asking what is probability a random chosen can has a floor. Okay. So we just define property has a floor for F is equal to P has a floor on the top plus P has a floor on the side. Ft is for floor on the top, Fs for floor on the side. Okay, and also because these two has intersection, we need to minus. Okay, minus P has a floor on the side and has a floor on the top. Okay, so we use the equation from the previous slides. So property has a floor on the side, 2%. On the top, 3%. Minus intersection tells us floor on both the side and top, 1%. Okay, equal to 0.04. Okay, so in other words, if we draw something, this circle means has a side, floor on the side, and this circle has floor on the top. Okay, so intersection here will be 0.01. Okay, and then we can figure out what is in this area and what is in these areas accordingly based on this information easily. Okay, so we'll see that in a moment. What is the property that it has no floor? Has no floor means what? Means anything outside these two circles. Okay, so has a floor means anything within these two circles. So property has no floor. It means complement of floor. So no floor is simply equal to 1 minus the property has a floor, which we just calculated is 4%. So that is 96%. Okay, so that means the chance it is outside this two circle is 96%. All right. If it is asking this, what is the probability that Ken has a floor on the top, but not on its side? His side, its side. Okay. So this is Ft, floor on the top. This circle is Fs, floor on the side. Okay. So we just calculated here, the intersection is 0.01. Okay. And the floor on the top, this whole yellow circle is 0.03. Okay. And the property has a floor on the top, which is this whole big yellow circle, which is 0.03%, 0.03 or 3%, is equal to this. This is the property has a floor on the top and has a floor on the side, which is this intersection. This is 0.01. Okay, plus this is what? This is the property has floor on the top, half circle facing down is and FSC. So that means FS means floor on the side, C means not. So not has a floor on the side. Okay, which is actually this area. Okay, so simply because the whole circle is 0.03, and the intersection is 0.01. So that areas, which is question, what is question asking is 0.03 minus 0.01, 2%. So sometimes you draw something like this, and you can see the correlation between, what is intersection, what is the, union, and something like this. Okay. So how we can find the probability? So we can use empirical study, okay, or we can use common sense to estimate based on equally likely event, like we just discussed. Okay, toss the die, toss the coin. Everybody knows if it's fire coin, the chance we have head is 50%. So that's the chance we have tail. 10% of US population has red hair. This is based on empirical study, kind of survey, for example. Okay, so select a person at random based on empirical study. P red hair is 10%. Okay, this is how we found probability. So next class, we're gonna use counting method such as combination and permutation to count what are the possible outcomes and calculate probability from there. Okay, so for today we have one last example, no, 2 examples. We have 3 slides left. Okay, so if we toss a coin twice, okay, what is the probability that we observe at least one head? Okay, so then we need to study what are the steps to perform that experiment. In this example, toss the coin twice. So we can see the first step is we toss the coin once. Okay, possible outcomes is we have head and tail. If the first outcome is head, then for the second coin, we could also have head and tail. Okay, as you can see here, underneath head, for the first coin, we also have head and tail. So we have head, head, and head, tail. Okay. If the first coin is tail, we also have head and tail. So we have tail, head, and tail, tail. And these are equally likely events. So every one of these 4 possible outcomes, they have 1/4 chance. So what is probability at least one head? So at least one head include head, 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 tail, tail, head, and not tail, tail. At least one head. Okay, so P, this one, and this one, added together, so 75%. Okay, so this is a very simple example of using counting method to do the calculation for probability. Okay, so another example, we have bowl of we have 3. A bowl has 3 M&M candies. We have 1 red, 1 blue, and 1 green. Okay, so select 2 candies as random. What is the probability that at least 1 red? Okay, so we use counting method. We count all the possible outcomes and we get the chance of the probability for each possible outcomes. Okay, if the first one is red, then the second could be blue and green. Okay, so then we have, red, blue, and red, green. The chance 1/6. If first is blue, so we could have blue, red, and blue, green. Also 1/6. So at least the red include red, blue, red, green, blue, red, and green, red. Right? We have 4. So 4 of events, and each event has 1/6 chance. So that is 4/6 of 2 or 3. Okay, so another example of using counting method. So if simple events in an experiment are equally likely, like the M&M candy and toss a coin, a die, then we can use this equation. PA is equal to the number of simple events in A over the total number of simple events. Okay, and next class, we're going to use counting rules such as combination and permutation to do the calculation. Okay, so let's stop here for today. We'll continue for section 2.2 Thursday this week. And Okay, so any questions? Again, next week we'll continue for online teaching. We'll start in-person teaching on campus. I think February 1st, Tuesday, after next week. Okay, I'll see you Thursday this week then. Okay, I will record the lecture and upload to YouTube and send you the link to Laurima so you can review the lecture. Right.